Recording is rolling. It is Tuesday, April 29. You guys have your stats packets from yesterday. Yesterday we did part A. I'll give you guys a recap, and then our main focus today is going to be part B. There is the part C we're going to save for tomorrow. And you guys remember the Z tables on the back, and we're going to also use that today. Okay. So how I pace steps today, we'll have a little bit of spare time actually at the end of class. So 5 or 10 minutes. So my earlier class had wanted me to go ahead and give them the final exam study guide. I do have them all printed out, but we're going to start going over the review on Thursday. That's 2 days from now. So we're going to finish all this stats packet, which is really a segue to quantum. We're going to take a pause on this. We're going to go over the final exam review, which is going to take us a few days. So with the study guide. Okay, go ahead. Yeah, you do that too. Yeah. All right, and then if you guys went to the format of the final exam, I don't know if you guys can remember the midterm, but it's the exact same format. So there will be, it's going to be all multiple choice. You get 50 conceptual questions, which are going to come straight off the study guide, which of course we're going to take a few days to go over pretty soon. And then there will be 10 equation-based questions. Maybe you have to do a little bit of algebra, set some equations, solve some things, and those will be 5 points apiece. But I will also give you the equations straight on the exam. So all you have to do is know how to apply them. Okay. And then I'll play a Mark Grober video at the end of class today. It's about 6 or 7 minutes long. It talks about NASA. He used to work at NASA. So there you go. Okay. So that's the plan. So everybody good with the agenda, what we're doing? Okay, so stats packet. Go ahead and pull out your stats packet. Well, everybody's got it out already. And so yesterday, you guys learned a ton of new concepts. Now, I told every single class, I said how many students are taking stats or have stats. And pretty much every single one of my classes, I had either 2 or 3 students who are taking stats or know something about this. So everybody else, there's a lot of new concepts. So I definitely got to give you guys a recap. And then I've been using this TI-30X2S. I know everybody has one of these because I have a class set. Now, if you have taken stats and you know how to do this with your own graphing calculator and you want to do that, that's perfectly fine. But everybody else, I'm going to highly recommend you have one of these in your hands right now, so you can hit exactly the same buttons that I'm hitting as we go along and get all the correct numbers. Right? Of course, all of us have different numbers, but same stories. Like yesterday, we're looking at populations. So I've got 5 dogs, 5 people, and 5 cats, and the metric we're looking at is height. Right? So story kind of goes like this. And if you pick one of your populations, let's say people, for example, and you said, oh, well, what's the shortest person, and how many are there? Okay, well, there's only one of those. And let's go by centimeter increments. So 1 centimeter up. Oh, there's a couple more. How about 1 centimeter taller than that? Oh, now it's even more, right? And when you get to like the average height, now there's a bunch of people that are sort of in the average ballpark. And then we start to get like really, really tall. Then, well, it's fewer and fewer and fewer, and it peters out. So you guys see this bar chart, like a histogram? Okay. And if you stand back and look at it, you guys see this bell curve emerges. I'm going to call this a normal distribution. We're making believe a little bit. We're doing some simplifications to say that height would be a good metric for something like this, but a lot of things are normally distributed. Okay. A lot of metrics. Okay. And how can I describe this bell curve? Well, I can describe it with 2 statistical quantities. That's the average. Now, for a normal distribution, the mean, median, and mode all end up being the same thing. Right. So, and you guys know how to find the mean. It's this formula right here. Right. So you add up all the values to divide by the number in the set, it gives you the mean average. Okay? And also the standard deviation. So do you guys remember that the middle of this bell curve is concave down, but the tails look like concave up? So the concavity switches. And guys, what's the name of the point where it switches concavity? Inflection point. And well, if you knew the gap, if you knew the distance from the mean to that inflection point, couldn't that be a way of describing how wide that bell curve is? Right? And that's one standard deviation. Now, how do you get standard deviation? I did print the formula right there, and we did walk through one of these examples yesterday. I think for heights of dogs we did. Okay, so here I have both calculations here. Here's the average height of dogs. Now, my 5 dogs are different than your dogs, right? And in the real world, guys, do you think in the real world, if you did this, you probably want like hundreds of dogs or thousands of dogs, right? Now, we're going to just go with a set of 5. We can force it to make sense, but just realistically, you probably want larger sample size than that, right? But I had my 5 dogs divided by 5 to get the average height right there. And then I went through dog by dog, took each individual dog height, subtracted the average. I squared that difference. I added up the 5 square differences for the 5 dogs. Then I divided that by the degrees of freedom, which is say the number of dogs minus 1. Okay? And then the last step is to take the square root. And out of that pops a number, that's your standard deviation. That's the difference between the mean and that inflection point, which tells you how wide the bell curve is. Right? But the calculator will automatically do that for you. And I showed you guys yesterday, we walked through this. And same thing today, we're going to do the same process. Okay? So the calculator, we also got this number, so we confirmed it. This does work. Okay? So we did this for dogs, for people, and then for cats. Now, if you look at these three bell curves, remember this is frequency on the vertical axis and height on the horizontal axis. So you could construct each of these bell curves out of bars, right? So that's what I did here, like a bar graph. Right? And we knew that the curve on the right was humans for two reasons. One is that it's furthest to the right. I know that people are generally taller than dogs or cats, but also there's kind of a medium variability. I know that dogs have more variability than humans in terms of height, but cats are all kind of the uniform height. So cats have almost no variability. Talking about house cats, right? So dogs be like middle height. Dogs are taller than cats, but shorter than humans on average. So they both have enough. But they also dogs have the most variability out of all these populations. So guys, how the curve is more spread out, and consequently that also makes it look shorter because each bell curve has the same area underneath it, which represents 100% of its respective population. Right? And cats are furthest to the left because they're the shortest. Cats are shorter than dogs and shorter than humans, right? On average. Right? There's a little bit of overlap from these curves, right? But also there's the smallest variability out of these populations. You guys see how it's the skinniest curve? It's because cats are almost all the same size as each other, okay? Which consequently also makes it look really tall. Okay, you guys remember that? And there was one more concept from yesterday, which is the z-score. Now, z-score, see if I got it spelled out somewhere in these notes. Right, so I have it here printed, but z-score tells you how many standard deviations an individual is from the mean for their respective population. Right, so this is something that you guys get to do today. All right, so we're eventually heading towards that. Okay, so if you have a z-score of 0, that means you are exactly average. You have no difference from the mean. Right? If you have a positive z-score, you're greater than average. If you have a negative z-score on some metric, you're less than average. And that's where this table on the back of the packet came in. It ranks z-score from negative 3.5 to 0 here, and 0 to positive 3.5 here. Right? Now, guys, once you get to a z-score of 3.5, that's 3.5 standard deviations above the mean. At that point, you've shaded in almost the entire bell curve. Yes, here it says 0.9998. That means at that point, from like the shortest being in your population up to that z-score of 3.5, you've accounted for 99.98% of the population. And the last 0.02% would be this extremely tall tail over here. That's who makes it to the NBA. Right, you guys got that? Okay. All right, so you guys go with the recap from yesterday? You have to remember all those concepts because that was a lot of new information. All right, you guys ready for part B? All right, part B. Oh, hey, look, it's the bell curve. And here's the three formulas that we were using yesterday. So mean, average, which you guys have known probably for many years. You guys have to take a mean. Here's standard deviation, which is new for most of you guys. Unless you've had stats, then you're familiar with that. We did one of those calculations yesterday. And then this one's for a z-score. Now that's for if you ask the question, where does a particular individual fit in among their wider population? Then that's where you need the z-score in that table in the back of the packet. Okay? You guys see how it all connects together? All right. Any questions so far? Any question? All right, so let's head down here. So we have a new story today. I have the volumes of liquid for several bottles. Now, my packet says 2-liter bottles, and yours maybe says something similar. Okay? So there could be another story we can attach to this. Like, suppose you work for some consumer protection agency, and you want to test, is there truth in advertising? They're advertising 2-liter bottles. Is it really 2 liters? Or is it less than? Or are they shortchanging their customers? And if so, by how much and how often? Okay. So on the technical detail, could you guys imagine back in the factory that there's a whole assembly line of bottles and they're being filled up one at a time? So it's like next one, next one, next one, next one, and every time the machine fills up a bottle, there's a little bit of variance. You guys think some are a little bit more filled and some a little bit less filled, right? So you can see how there could be a little bit of variability. Okay? So we're going to grab some bottles off the shelf. Now again, if you actually work for the government one day and you're actually doing this, then do you think you probably want to pick like hundreds of bottles off the shelves? Right now, we're gonna make a little shortcut here. So we're gonna grab 5 bottles. We're gonna say that somehow this tells us about the population at large. All right, so it is calculator time. Everybody got a calculator? Calculator. Now let's clear out the data from last class. So turn on your calculator. I'm going to hit second and then 0, which is second reset. Whoops. Second 0, which is second reset. It says, do you want to reset? No or yes. Now scroll over to yes. Right. Guys, along the way, make sure you're hitting the same keys I'm hitting. If you're ever not sure what's going on, then raise your hand and stop me and I'll get you caught up. So everybody hit yes? Everybody cleared out the memory on their calculator? You guys good? Cleared it up? All right, so clear all that. We need to input these 5 bottles. So do you guys remember right above the cosine, there's a key that says data? And just above that in white letters, it says stat. We need to access that function, that key. So hit second stat. And on your screen should pop up 1 variable. Okay. Does anybody not have 1 variable on their screen right now? So everybody has 1 variable. Click enter. So at that point, the word stat pops up on your screen. I see it right there. It says stat. It also says degrees. I don't care about that so much, but I definitely care it says stat. So everybody says stat. Is that correct? That's right. Now hit the key that says data. Again, it's the one right above the cosine. It says data. And up on your screen pops X1. So does anybody not have X1 on their screen? So everybody's seeing X1 right now. Okay. Now, at this point, go ahead and plug in your first bottle. My first bottle is 1972 milliliters. Okay, so we took this back to our lab, we poured out the contents, we measured it. I'm getting that many milliliters. Okay. Scroll down. Frequency 1. Yep, there's only 1 of those bottles. Again, you could imagine in the real world, if you have hundreds of bottles, you think, oh, there might be like 19 of those bottles. You punch in 19 of them. But I only have 1, so I'm going to leave it as frequency 1. Scroll down again. Ooh, X2. Punch in my second bottle. Scroll down. There's only 1 of those. Scroll down again. Punch in my third bottle. Scroll down, scroll down. Punch in my 4th bottle. Scroll down, scroll down. Punch in my 5th bottle. Okay, at this point, I have all 5 bottles loaded into my calculator because that's 5. And then if I scroll down one more time, frequency 1, it's only 1 of those. Okay. Okay. How about you guys? You guys have all 5 bottles in your calculator? Everybody's got all 5? Everybody's good? Okay. Now, we're going to let the calculator crunch all this data, the average, the mean, the standard deviation. You guys see the key to the right of data that says StatVar? That's StatVar. Go ahead and click StatVar. Boink, StatVar. And it says n equals 5. So, yep, there's 5 bottles. So, actually, everybody should have 5 bottles. Everybody's got 5 bottles? Right. Scroll to the right. There's X bar. Guys, what does X bar represent again? The mean. Yeah, mean average. So mine is 1989.2. I'm going to copy paste that right here. 1989.2 milliliters. Ooh. So they're advertising 2000. They're only supplying 1989. It looks like this company is shortchanging their customers a little bit. Okay. But to make more sense, if I want the full explanation of a bell curve, I also need the standard deviation. Oh, how do I get that? Scroll to the right one more time and the calculate. Whoops. Wait, what happened? Oops. Okay. Go back. Right. Oh, it says S sub X. Now mine says 15.9. I'll call it 15.9. 15.9. Remember, that tells you sort of how wide your bell curve is. Think of that like a plus or minus factor. Right. Now, there's a detail that I mentioned yesterday. I know I gave you guys a bunch of new info yesterday. But see if you either remember this from yesterday or if you can figure out it right now by looking at this bell curve. You guys see this bell curve? So here's my question for you guys. If you're working with my bottles, my average is 1589. So isn't that like that, the middle of my bell curve right there is 1589? Is that true? Right. What if I do plus or minus, can I round that number to about 16 milliliters? Is that okay? What if I do 1589 plus or minus 16 milliliters? How many bottles, suppose there was thousands of bottles on the shelf, how many bottles would that account for? What percentage? Or in general, because isn't 16 milliliters 1 standard deviation? Because in general, for any population, any metric of anything, if it's normally distributed, if you start with the average and you do plus or minus 1 standard deviation, that covers what percentage? 68, that's right. Because 34 and 34 is 68. You guys see that? Right? If you take in stats, this is called the 68, 95, 99, 7 rule. So plus or minus 1 standard deviation, plus or minus 2, plus or minus 3. Right? And at that point, you've covered almost the entire bell curve. And anything you haven't covered would be like either extremely on the low end or extremely on the tall end. Okay? You guys know that? Okay. So for me, see 1589 minus 16, 1589 plus 16, that covers about 2/3 of the bottles, right? Right? Right. Next question. So let's say you pick another bottle. We're not going to mix and match with it. We'll go ahead and leave these numbers locked in place. We're going to draw another bottle. Now, where does this last bottle fit within the scheme of the other bottles? Well, that's what we need z-score for. So it's z-score time. You guys ready to calculate a z-score? So formulaically, in general, we're going to take the individual value, we're going to subtract the mean, and take that difference and divide by the standard deviation. I'll call it S. So with my numbers, it would go like this. I'm going to take this individual bottle right here, some number of milliliters, subtract the mean, which is this number right here, also milliliters, right? Now, right away, I see this bottle is above average filled. You guys see it's above average filled, it's going to give a positive z-score. But how much above average? Are we talking about, like, if I have thousands of bottles, is this one just a little bit more than average? Is this one of the most filled bottles ever on the shelves? The only way I can make sense of that is I have to say, well, what's the standard deviation compared to that? I need a count of the number of standard deviations above the mean is this particular bottle. You guys remember that? Right? So divide by 15.9 milliliters, and that'll give me a count of the number of standard deviations above the mean. Is this one particular bottle? Okay, you guys up to where I am? So I'm gonna throw that in the calculator and see what I get out of this. So open parenthesis, that minus that, close parenthesis, and then divide by the standard deviation. I'm getting exactly this integer value right here. I'm gonna plug this right here. Right. Oh, guys, what is milliliters divided by milliliters? What is that unit? How about it's not, there's no unit at all? Is it unitless? So it's just, for me, it's 2.0. Okay, is that okay? Right. And actually, it's good that it's unitless because what you've effectively done is you've found a number that can fit on this standard bell curve on this table in the back, which of course has no units. Because, guys, isn't it true that this very generic bell curve with the z table could apply to kind of any metric? Right. This could be temperature of rabbits. This could be blood pressure of giraffes. This could be like any of those could be normally distributed. They could all be described by this table. Right. Right. Here I have volume of water in bottles. Right. Is good. Right. Now your number right here. If you're tracking, if you're doing it right, I did design this page so that this is only one of 7 numbers. You have an integer. You either have -3, -2, -1, 0, 1, 2, or 3. And mine, of course, is 2. Right? But everybody should have an integer. Does anybody not have an integer value right here? If you get 1.99, just go ahead and call it 2. Okay? If you have -1.01, call it -1. Okay? It should be really, really, really close to an integer. That's good? Okay. All right. Now, what does that mean? I got one more question about these bottles, and really, let's extend that to 2. See where it says what percentage of bottles contain less liquid? Okay. Let's throw in one more question. What percentage contain more? Right. And you guys see that those 2 questions really go hand in hand. If you know one, you immediately know the other. All right. Now, how we're going to answer, well, both those questions, but one at a time, is this table in the back. So find your z-score. Now, remember this table, the left half of this table is a little less than average, has negative z-scores. The right half of this table is more than average, has positive z-scores. All right, and right at the top is 0 right here. All right. So I'm going to go down to 2. So I have 2.0. Bam, that's right there. I see 2.0 right there. Get that? Okay. And you can get more granular going across. 0.00, 0.01, 0.02, 0.03, 0.04. But since all of us have basically integer values, then it's just this first column right here, which mine says 0.977. Guys, 0.977. What is that as a percentage? 97.7%. Right? And do you guys see how it maps onto this bell curve? It's how much is shaded up to the z value of 2 in my case. This is 97.7% of the bell curve. Okay? Which answers the question we're trying to ask. It says, what percent contain less than this particular bottle? Well, if you have a z-score of 2, just like I do, then the answer is 97.7%. Right? Right? Let me do some other ones. Just make sure you guys got this. If you have a z-score of 1.0, the answer would be, is that 84%? If you have a z-score of exactly 0, doesn't that put you at exactly the 50% mark? If you have a z-score of -1, that's about 15%, 15, 16, something like that. If you have a z-score of -2, that's about 2%, okay? Which is getting pretty extreme out on the tail. Okay, you guys got that? Does anybody have any question about their z-score and their table value? So everybody's okay? Everybody's up to where I am? Okay. Because I do have a follow-up question that I handwrote right here. Guys, if my bottle is so full of water that it has more water than 97.7% of thousands of bottles on the shelf, that means how many bottles contain more water than my bottle? 2.3%. That's right. Because don't you just subtract that from 100? Right? There's 100% of bottles. 97 have less. Okay, you guys that? Okay. Right. All right. So let's move on to the lab portion of this. So it's time for you and your friends to get together. You guys can have a height contest. Not really a contest, but yeah. All right. So you guys got some meter sticks. You guys got some meter sticks within reach. Okay. So I'm going to have you guys measure your height in centimeters. In centimeters. Careful, you're not measuring in inches. So, guys, what would be a more reasonable number? What's more reasonable? 67 or 167? What would make more sense for that box right there today? Let's go 167. That's like human height. If you have 67, then well, you can be one of the dwarfs in Snow White. So let's go with 167 because that would be how many centimeters, right? Not inches, but centimeters. Got that? Okay. Now, can you guys find your height and 4 friends today? And punch those numbers into the calculator. Maybe you want to clear out the data that's there for bottles. And I want you to find what is the mean height. Now, we're going to make believe that you and your friends today are representative of, say, the entire school. And if that's true, what's the mean height of a student? What's the standard deviation? Can you find those from the calculator? Let the calculator crunch that for you. Okay. Then take your own height, whatever your own height is, in centimeters. Find your z-score and context for all your friends. For those 12. Okay. And you guys see this very last question. What percentage of people are taller than you? Ooh. Guys, notice it says taller, not shorter. So the fact that it says taller, not shorter, do you pick the number straight off the z table or do you have to subtract it from 100%? How about the last thing I said? That's more framed like this question that I hand wrote down here. Isn't that more in context like this right here? You guys see that? You have to subtract from 100%. You guys see why? Because it's taller, not shorter. Right? You're not looking for the part that's shaded, like it's shown on this bell curve. You're looking for this little white tail here, which is 100% minus that shaded part. Okay? And the table tells you the shaded part. You guys good? All right. So just to round out today, I'm going to walk around, help you guys out. We're pretty good on time. I will also give you guys this final exam study guide. Don't lose this. We're going to start going over this on Thursday, a couple days from now. And then the last 2 minutes of class, I'll play you guys Mark Rober video. It talks about NASA. He used to work at NASA. You guys learn a little bit about NASA. A little bonus right there.